Hi students, welcome to Year 11 Chemistry and the Introduction to Quantitative Chemistry module. This is video number 8 looking at empirical formula of a compound. So our question this time is, how do we know what formula to use when we're determining molar mass? Now this might sound like a fairly simple concept, and certainly for molecular substances it pretty much is. But for substances that form networks or arrays, we have to find an alternative in order to help us to understand what values we're going to actually use. And what we need to do is find the simplest whole number ratio in which the component atoms of a substance are combined, and then use that symbol for each type of atom in order for us to work out exactly what formula we want to be using in our calculation of molar mass. This simplest whole number ratio idea is known as the empirical formula, or EF. Because it's the simplest whole number ratio, there are times when the empirical formula is the same as a molecular formula, but other times where it is not. And so we'll just have a look at a couple of examples in this video to make sure that those concepts are clear. Firstly, non-molecular compounds such as ionic networks have empirical formulae only. There is no discrete atom, there is no discrete CuSO4. All of those copper ions, cations, are going to be surrounded by the sulfate anions, and they form a network such as we looked at in our previous topic. And as a consequence of that, we need to sort of reduce this network or array down into its smallest component. And that smallest component, that empirical formula, is CuSO4. That is one copper cation to each one sulfate anion. And this happens for all ionic networks. Same thing in the example for zinc nitrate. Of course, the difference here is the ratio 1 zinc to every 2 NO3 anions. So all of our ionic networks are formed in this way. Incidentally, so are metallic substances. So we know that metallic bonds form in metals. So when we look at something like sodium, we don't regard sodium as being this array of sodiums, which it is if we were to think about it in terms of the solid structure. When we're looking at calculations based on the number of moles, we regard sodium as being the simplest breakdown of that array is a single sodium atom, and therefore we can calculate its molar mass based on just that one atom of sodium. Now, where we have non-molecular compounds, the formula mass is the same as the empirical formula mass. So this is what I've just mentioned above. So there is no other way of writing CuSO4 other than CuSO4. This is the same for magnesium, and it's also something that we find in a number of different types of other networks as well, such as, for example, carbon in diamond, or even silicon dioxide. So again, these are all examples of non-molecular or network substances, and we reduce all of these back to their empirical formula when we're calculating a formula mass or a molar mass. However, there are also some molecules, and molecular formula may or may not be the same as the empirical formula. So I have a couple of examples here to kind of show you the difference between these. Carbon and oxygen is a good example because carbon can form the compound carbon monoxide with oxygen where the ratio is 1:1, or carbon dioxide where the ratio is 1:2. These are empirical formulae, and they are also molecular formulae. The two are identical, and we would calculate the molar mass of carbon dioxide by adding together the mass of one carbon and then adding 2 lots of the masses of each individual oxygen. We would only need one of each for the calculation of carbon monoxide. But when we look at octane, it's slightly different. The empirical formula for octane is the simplest whole number ratio. In this case, that's C4 H9. I can divide both 8 and 18 by 2, and that gives me my smallest whole number ratio for this particular compound. So octane has the empirical formula C4H9. Now obviously this does not represent a molecule of octane, and therefore we need to use the molecular formula, not the empirical formula, when we are calculating the molar mass of octane. So one of the important things for us to remember is that molecular compounds may not always be in the simplest ratios, but we still need to make sure that we identify how many of each atom we have, what the relative mass of each of those is, and then add them together in order to get our molar masses or our molecular masses. Again, there's a lot of interesting concepts here that are much easier understood through practice, so you should get plenty of that in class. Thanks for watching.